Okay, so before the lectures start, I should say that there's a lab submission next week, okay? So I posted on Moodle already just a few minutes ago. And secondly, next week there will be no lectures, okay? If you check the syllabus, there's no lectures on week 6. However, the labs and tutorials are still as usual, okay? So week 6, no lectures, but still have labs and tutorials, yeah? So you don't have a full break like before, you have only half a break. Okay. And question? I think it depends on the subject. Okay, so you have to check with the different lecturers, different syllabus. See, because the idea is in the previous schedule, you have 24 lectures, 12 weeks, and now we still have 24 lectures, but over 8 weeks. It means that you have, 2 weeks no lectures. Okay. So the number of lectures is still the same, but the time is different. Okay, so last time we talked about the, like how to solve nonlinear equations in using 2 methods. Well, actually 3 methods. The first is the bisection method. So bisection is, you have to assume that the function is continuous, and you just keep dividing the intervals until 2, by select the midpoint, and then you go further, by checking the signs at each ends of each sub new intervals. Yeah, so then you go further. So if the left sub intervals has opposite signs, then you choose this one to be the new an plus 1, bn plus 1, and so on. Okay, and then the second method we discussed was the fixed point iteration. So fixed point iteration is when you have x equal f of x. Yeah. So before you have f of x equals 0, but here you have x equal f of x. And then the fixed point iteration is you just define x1 to be f of x0 and x2 to be f of x1 and so on. Yeah. And in order to get convergence, then you have to have g prime and x star is, the derivative at x star has to be less than 1, so it's a contraction. Otherwise it will blow up, right? Because, if it's not a contraction, then eventually it can go to infinity. And the contraction, it just means that you expect that g prime and x star has to be less than 1 in absolute value, okay? And then we also discussed about Newton method. So Newton method was, you can view it in 2 ways, okay? The first way is, you can expand the function in terms of Taylor series, right? Around xn. Yeah, so this is the usual formula for Taylor expansion. And then you set x equal x star. Okay, and then you ignore the higher order term. Then you have this equation. And then you set xn plus 1 to be equal x. Okay, so then xn plus 1 is the solution of this linearized equation. So another way to look at Newton method is you draw pictures. Okay, so you draw a curve like this. And so this is xn. Then you plot a tangent line. And the tangent line that will cut OX at xn plus 1. Okay? And the next step, you just plot a tangent line here, then plot it down here, then it will cut at xn plus 2, and so on. Okay? So how do you find xn plus 1? Well, remember we have to find the equation of the tangent line. Yeah? So remember the equation of the tangent line is just exactly this equation. Okay, so it's the equation of the tangent line. And you set it equal 0, and you find out exactly xn plus 1, the same formula. Okay? So that is the review of the last lectures on Wednesday. So now we will talk about the errors. So you will see that if you use Newton method, it go to the solution of the function is very fast. Okay? And we try to explain why it's the case. So then initially you can view Newton method as a fixed point iteration with the right hand side to be this function. Yeah? Remember, so you have a xn plus 1, it's just xn minus fxn over f prime xn. So you can consider this one to be g of x, the whole thing here. Okay, and if you do something like that, you can check that g prime. Yeah, so g prime, by apply the quotient rules, you can get out g prime like this. And you see g prime x star is always equal 0. Because if you put an fx star here, it always equals 0. So it's a very good contraction, because what you want is you want the absolute value less than 1. But this one is equal 0. Right? So that's the best you can get. So actually, the ratio en plus 1 over en, take the limit, it will go to 0. But we can do better. So the theorem is, suppose you take en plus 1 over en squared. Okay? Then it will converge to some fixed number. And fixed number is given by this. F double prime over 2f prime. So before we prove this, so let's see, what is the consequence? What is the significance of this result? So now, just before we prove it, okay, so just discuss a little bit about the results here. So remember in the fixed point iteration, so fixed point iteration, yeah. Then you have en plus 1 equal roughly g prime x star, en. Yeah? And so now in Newton method, you have en plus 1 equal, something like f double prime x star over 2 f prime x star en squared. Okay? So now, which one is better? So now suppose I have E0 is like 0.5, right? Yeah? And then so then suppose that you fixed point, yeah? Iteration. Then E1 will be some constant, so suppose I denote this one to be some constant, so alpha g prime, alpha en, yeah? And this one is beta en squared, yeah? So alpha and beta just some constant. So now suppose fixed point, then E1 will be alpha E0, right? So what is alpha? Well, maybe make it simple. Make this one is the same, yeah, alpha, yeah. Just make it. Suppose you can make the two constants are the same, yeah. So then this one is alpha times 0.5, right? And then E2 will be alpha, E1 will be alpha, then alpha 0.5, right? So what is alpha squared? 0.5. Yeah? And so on, right? So now suppose you use Newton method. So suppose you have Newton method. So suppose you start with E0 equal 0.5 as well. Yeah. Then what is your E1? So E1 will be alpha E0 square, right? By the theorem. Yeah. Suppose you can prove the theorem. So this one will be alpha 0.25. Okay. And then E2 will be alpha E1 square. So will be alpha times, alpha square 0.25 square. Yeah? So what is alpha cube 0.25 square? So which one go down to 0 faster? So which one go down to 0 faster? Newton method, right? So you can see that because everything is smaller than 1, yeah? Because here we have to assume that alpha is smaller than 1, alpha is smaller than 1. Otherwise, we blocks up. But you see, like, because it's smaller than 1, so therefore, Newton method will go down to 0 faster. Because the power. So you see, do you see it? Like you can see it before you run the program. I mean, if you have you compare Newton and fixed point iteration, then Newton will be faster. And so the key is this power and also this power. So this is power 1. Sorry, this is power 1, but this is power 2. Yeah. So we will discuss about that later. But before we discuss how do we prove this. So we prove this by, just Taylor expansion. So first, you use Taylor expansion around xn. Yeah? So remember, what is Taylor expansion? So why I say that is the Taylor expansion. So now suppose you have Taylor expansion is f of x around xn, yeah? So will be f of xn okay, so plus f prime xn x minus xn plus f double prime xn over 2 x minus xn square plus f triple prime xn over 3 factorials xn cube and so on. Okay. So now I just let x to be x star. So x to be x star. So the consequence is f of x star will be equal 0 because we assume that x star is the 0 of the function, right? And then because we assume that en to be xn minus x star. Okay, so therefore this one will reduce to, well, this one is still the same, but this one will reduce to minus en. Yeah. So that is how I got this equation. Okay, so now, so that is how I get 0 equal f xn minus f prime xn en plus, well, because this one you square, so the minus square become plus again, yeah. So f double prime en square, and I ignore a higher order term, so I just write a big O notation. So that is exactly this equation. Okay. So far so good, yeah. And now we use the definition of the Newton method. So what is the definition of Newton method? So this is the first equation, so we got it, yeah. So the second equation is, remember we got xn plus 1 equal xn minus f of xn over f prime xn. Okay, so this is the Newton method. And now you just minus x star on the left and you minus x star on the right. You know, so this is the same, yeah? So then this one is nothing but En plus 1. And this one is En, you know, so by definition. Yeah, so that is how you get this equation. Yeah, so En plus 1 is En minus fxn over f prime. Okay? Yeah, so far so good. And now I just cross multiply it. So this one is still f prime. Cross multiply and then you combine two terms. Yeah? So that is how you get this equation. And now how do I move from this step to this step? How do I move from here to here? Huh? From the second to the third line. So you agree that I can move from here to here, right? Yeah? And then now how do I move from the second to the third line? Yeah, just use this one. Yeah? You use this one because this is 0. Yeah? So then, you know, I mean, you can move, I mean, those two terms into the left, then you remain the right-hand side. So this is what you get here. Okay? So far so good, yeah? So you plug it in. And now the final step is you just divide it by En square. Yeah? So divided by En square on the left, then you have this one. And then you divide it by En square, then this one only the ratio, and this one you divided En square, you have only En. Okay? So now we have the final here. So now you just let xn go to x star. Yeah? So xn go to x star, then, you know, I mean, xn will go to x star, this one become f double prime x star. Yeah, and this one become f prime x star. Okay, and what happened to this one? What happened to En? Go to 0, right? Because En is just xn minus x star, so x star, xn go to x star, this one go to 0, and so that is the theorem, right? So the statement of the theorem is the limit of this one equal 1/2 f double prime x star over f prime x star. Okay? So that is the theorem. So now you go to the, you know, go back to the MATLAB and you can implement, you know, another example. So here you compute the error, so the En is xn minus x star, yeah? And then you compute the ratio, En square over En plus 1 over En square. And you see that it approaches a constant, right? So minus 1.3 something, okay? But why it becomes so big in the very end? So why it becomes so big in the very end here? No, but this one, it doesn't go to infinity. This one, xn is stable. But only the ratio become very big. You see, like by the theorem, yeah? So this ratio has to be a constant, roughly a constant. This constant might be minus 124 something, right? But then suddenly just, you know, jump to 1 million. And why is that? You see the problem here? So the theory is correct for 2, 3, and 4. And suddenly it's just wrong at n equal 5. And why is that? Huh? You passed the solution already. Well, I mean, you see, if you check the solution is here. So only the ninth digits changing, right? Yeah, but you see the first 8 digits are the same. See, the trick is, look, what is the errors here? The error is 10 to the minus 17. And what is machine by epsilon? What is machine by epsilon? 10 to the minus 16. Yeah, so this one, the error is below the machine epsilon already. Okay, so all the calculation is not correct anymore. So it's not because the theory is wrong, just because now it's based on the limit of the floating point representation. Okay, because the errors go down smaller to epsilon, it cannot do any further computation. Yeah, so then this one, doesn't follow the theory anymore. Okay, but here still okay, because you see this one minus 2, minus 3, minus 6, minus 12, so everything is okay. Okay. So Newton method will converge is faster when the initial guess is close to the exact solution. Yeah, but if you don't choose the x0 correctly, then it might not converge. Okay, so you can see it from the pictures, right? I mean, suppose you you don't choose the correct initial guess, then the tangent line can go further away, right? So you can plot the line and you can see it. So now the problem with Newton method is sometimes you don't have the derivative of the function, yeah, and Newton method depends on the derivative, right? Because if you go back to the formula, you have f xn over f prime xn, yeah. So what happens if you don't have the derivative? Fixed point iteration, you don't need the derivative, right? You just plug it in. Bisection method, you don't need the derivative either. But only Newton method, you get fast conversion, but the price is you have to supply the derivative. Okay? So what happens if you don't have the derivative? So people have invented the secant method. Yeah? So the secant method is you approximate the derivatives by the divided difference. Okay? So remember, the divided difference formula. But actually you can plot the pictures. You see, before you have f prime here, but now f prime is replaced by this divided difference coefficient. Okay? And essentially, you can draw pictures. So this one is your xn minus 1, and this is xn. Yeah? Then, the divided difference coefficient is the slope of the line. Yeah? So the slope of the line here. So this one is f of xn minus f xn minus 1 over xn minus 1. And it's a divided difference over 2 points. Okay? So you approximately see like before you want the derivative at this point, yeah? So of the function. But now we don't have it, so we approximate the slope of the tangent line by the slope of the secant line that connect the 2 points. So it's not accurate, but still you don't have to compute the derivative. Yeah, and the formula is exactly similar to Newton method, but you replace the derivative by this divided difference. So now if xn is close to xn minus 1, so if the 2 points are close to each other, then it will approximate the derivative at f prime. Okay, so this one is the approximation of a Newton method. And the secant method, because the slope of the secant line that connect those 2 points. Okay? So the secant method doesn't require derivative. What the price you have to pay is the conversion is somewhat slower than Newton method. Yeah? And you can see that, for the previous equation, you plug it in secant method, then, the En plus 1 over En squared, the ratio of the errors, it just slowly go up to 1 point something. But, it's not the same constant. Okay? And we can prove that, the En plus 1 over En times En minus 1, yeah, the errors at step n plus 1 over the product of En minus 1 will go to a fixed constant. Okay? So that is the theorem. So you see, before a Newton method, you have En plus 1 over En squared. But now you just have a product of En and En minus 1. Okay? And the proof is, so it's a bit tedious, but you can follow the step. So here, it's just a definition of En plus 1, the definition of En plus 1, yeah? And now you replace Xn plus 1 by the formula of secant method, okay? And now, from here to here, so from this step to this step, you just move X star here to the left, yeah? So I just put X star here, I move it here, so I got Xn minus X star. And then, because X star is a solution, so X star equals 0, so I just minus 0. So Fxn minus 0 is the same as Fxn minus Fx star. Okay? So that's why I got to this step. And for this step, I just multiply and divide it by Xn minus X star, so I have this one. Okay, so far so good. And then from here to here, I just take Xn minus X star to be the common factor. So Xn minus X star is the common factor, then I have 1 here. And then, so what is this one? So this one is, if you remember the formula for divided difference, so this one is just a divided difference coefficient of Xn and X star. Okay, so that's why we replace this quotient by this one, finite difference over X star and Xn. Okay, so far so good, right? So now this one is En, right? Because this one Xn minus X star just En, so I'll replace by En. Yeah? And now how do I move from here to here? Okay, so now how do I move from this term to this term? So I have Xn minus X star 1 minus F X star Xn over F Xn minus 1 Xn, right? And I want to make it the same as this right hand side, right? Well, so initially I replace this one by En. Yeah, so it's okay, right? So dot, so previous step, so this one is En. And now I just cross multiply. So I have F Xn minus 1 Xn here minus Fx star Xn. Yeah? So is it the same at the right hand side yet, or? Yeah, so it's the same, right? For except that you multiply and divide it by the same term again. You multiply by xn minus 1. So actually, I mean, from here to here, it's a combination of two steps. First step is you just cross multiply this to get this over this. But then you have to multiply and divide it by xn minus 1 minus x star and divide it by xn. Yeah, so you see here you just multiply by xn minus 1 minus x star, right? So you have f xn minus 1 xn here, f x star xn. So this term move here, and then this one xn minus 1 over x star. Yeah. So that is how I get from here to here. Okay, so now what is this one? So this one is en minus 1. So what we are doing is we try to rewrite en plus 1 in the form of en times en minus 1 multiplied by something. Right? So that is the purpose, because that's what we want to prove. Yeah? And now I got the product of en and en minus 1 already, right? And now what happened to this term and this term? So this term will stay the same, yeah? How about this one? So this one, if you remember the divided difference formula, yeah? And this one is just a divided difference over 3 points. Yeah? xn minus 1, xn, and x star. Yeah? So in the interpolation chapters, I mean, this is exactly the formula for divided difference over 3 points. So that's why we replace this one by divided difference over 3 points. Yeah? So now you just take the left hand side here, you divide it by en times en minus 1. Then you just get this ratio. Okay? And now, I mean, if you remember the mean value theorem for divided difference, yeah? So remember the mean value theorem for divided difference some times ago. So let's see, now you have f of xn minus 1 over xn, yeah? So this one is just f of xn minus 1 minus f of xn over xn minus 1 minus xn. Okay? And so this one is, I mean, if xn minus 1 go to xn, then this one just go to derivative at the point x star, right? So x star is the limit. Okay? So, I mean, this is a secant line. It looks like this. So the secant line, you have xn here. Sorry, xn minus 1 and xn. And when the 2 points collapse to each other, then you just go to the tangent line. So you go to f prime. Okay? And similarly, the divided difference over 3 points go to the second derivative. Okay? Why is that? Well, because, I mean, if you look at this one, you look at the formula, yeah? So that is, so now how about the second term? The second term is f of xn minus 1, xn and x star, right? So what will be the ratio of f xn minus 1, xn minus f x star xn over xn minus 1 minus x star, right? And you see in the limit, then this one go to f prime of x star minus f prime xn, yeah, over x star minus xn. And you see, then this one in the limit go to f double prime x star, right? So over 1/2. So where does the 1/2 come from? Well, but maybe, you can think in terms of the Taylor polynomials. So maybe this one is not a valid reason. So this one is valid, yeah, because the ratio go to f prime, yeah. But I mean, if you look at the Taylor polynomials, yeah. So if the Taylor polynomials around x star, you got like f xn plus f double prime xn over 2 plus so x minus xn, yeah, and sorry, maybe go back to the Taylor polynomial, yeah. So suppose you have f of xn, so f of x here, yeah, plus f prime xn x minus xn plus f double prime xn over 2 x minus xn square, right? Yeah. And now plus some higher order terms, yeah. And now if you remember the divided difference formula, right? So if you interpolate over xn minus 1 and x star, then you have, f of xn plus f of divided difference, yeah, xn minus 1 x minus xn plus f xn minus 1 x star, right? X minus xn and x minus xn minus 1, okay? And now sorry, I missed the yeah. Okay, so this is Taylor polynomials, and this is the interpolation polynomials. Okay, and so when xn and xn minus 1 go to x star, yeah, then you have the polynomials, the Taylor polynomials will be the same as the interpolation polynomials, okay? Will be the same as the interpolation polynomial. And therefore, you see the coefficient for the quadratic will be the same. So then you will have f of xn minus 1, x star will go to f double prime x star over 2. Okay, so that is how so I think it makes sense, yeah. Now these are Newton form. Newton form of interpolation. Yeah? And you check only the degree 2. Yeah, the degree 2, then they have to be the same. Yeah, and then that is how I get the first limit here. So the limit, then this coefficient will go to 1/2 f double prime x star, and this divided difference will go to f prime, and that is how you get this final results. Okay. So it's a bit tricky, but if you go step by step, then it just follow from the previous discussion. Okay. So any question about secant method? So in MATLAB there is a function called f0, and f0 they use a combination of bisection secant method and then interpolation, and then you can use it to find the zero of a polynomial. So you just define f as an anonymous function, and then you give initial point, initial guess, and we'll find the solution for you. Okay. So sometimes you can have two solutions. Then you have to give a different initial guess. Yeah. So just give the zero that close to your initial guess. So then what method you should choose? Well, I mean, it's not easy to choose which method, but usually they use a combination of many methods to find a solution. So fixed point iteration is slow, but it's very efficient when you have a small g prime. Okay? And Newton methods is very efficient, but you have to find the initial guess very close to the solution. So sometimes you don't know the exact solution, then how do you stop? Right? You can stop when the gap between when the gap between two iterations are very small. Or you can stop when the value of f at xn is smaller than some tolerance. Okay? So you can choose, the relative errors in the successive iteration smaller than some tolerance as well. So many ways to stop the iteration. Okay? You see, related to the point I discussed before we proved the theorem. So there is an order of convergence. Yeah. So order of convergence is the largest power nu. So that when you take the ratio en plus 1 over en to the nu, when you take the limit n go to infinity, it's a fixed constant. Okay. So for Newton method, what is nu? So what is nu for Newton method? We just proved it before the secant method. So what is the order of convergence for Newton method? Huh? 2. Yeah? So because you have en plus 1 over en square equal a constant, yeah? So Newton method, order of convergence is 2. And how about fixed point iteration? So what is the order of convergence for fixed point iteration? 1, yeah? Because en plus 1 is just a constant multiply en. And so that is how we say it. So when nu equal 1, we say that linear or first order convergence. Okay? And then when nu equal 2, we call it quadratic convergence or second order. So how about secant method? What is the order of convergence? Is it 1 or 2? Or something else? Huh? So for secant method, what is the order of conversion? Is it 1 or 2 or something else? Huh? Golden ratio. Okay, you've read the lecture notes, okay? so Newton, the secant method, the people can prove that it has order of conversion with the golden ratio, okay, which is bigger than 1 but less than 2. Yeah, and in this case they call it superlinear conversion, okay? So they don't call it quadratic, but they call it superlinear. So more than linear, linear is order 1, quadratic order 2. But this one is between, yeah, so. Okay, so now, so far we have discussed only Newton, we have discussed only function of one variable, okay? So you have 3 methods, but we apply only to function of one variable. So what happens if function has more than one variable, right? So remember in this, the very first slide, we could have a system of equations, yeah? So in terms of the GPS navigation equation, you can have 4 equations like this, yeah? And how do we find the solution of the system of nonlinear equations, okay? So maybe we take a break for 5 minutes and then we discuss that. Is it okay? Yeah? Okay. Yeah, because more slopes and more arms. Yeah. So, but you mean like how direct it is? Yeah. Because it depends on the number of slopes per clock cycle. Right? Because suppose you have a 3 gigahertz CPU, and it can do 1 operation per clock cycle, and it can do 3 billion operations in 1 second.
Let's just show you the lab. The second question. It didn't seem like there was no voice 2 times.
Yeah, because you know why? Because in the computer, it's doing many things at the same time. So analytical estimate only gives the ideal condition. Because inside the computer, the CPU doesn't. It has the different side.
So just on average.
Not exactly. this one. Oh, why do I get it? because I is yeah. Because this one is this one. And this one is and then this one. No? See, because when you have y transpose y, just equal y1 to so just like this. Yeah. Okay. You can have it. You can have it. Okay, so we have to go back to the lecture. So now, before we talk about Newton method for 2 or 3 or 4 or n variables, let we talk about Taylor expansion in n variables. So anyone have done like vector calculus? Yeah, function of 2 and 3 variables. So have you seen this one? If you haven't seen this, then maybe remember this is the formula here. So if you have a function of n variables, okay, then you can approximate, like the value at x1 plus some small h1 xn plus hn by this approximation, okay? So you see, this one is very similar to Taylor polynomials, except that now you have all the partial derivative of order 1. Yeah. So, so what happened is, how do I interpret it? So now, let me draw your pictures. So suppose just take 2 variables. Okay. So the function is f r2 to r. So what is this function? So this function is a surface, right? So this function is just a surface, something like some surface like this. I'm not a very good artist, but roughly this one is f of x and y equals some z. Yeah, so this is z, x and y, right? Yeah. And so there is a vector called gradient. Yeah, so gradient f is partial f with respect to x, partial f with respect to y. Yeah. So anyway, so the gradient, could be point downwards, it could be point upwards. Suppose point upwards like this. So this is a gradient vector. Then you have a tangent plane. You have a tangent plane, yeah? So that tangent plane, everything on the tangent plane is nabla x, dot x equals 0. So this one actually on the tangent plane is a nabla x dot x minus x0. Alright, this one is x1, yeah? So suppose so this one is the point x1, x2, yeah? So x minus x, well, so we can have x and y, so maybe y minus y1, yeah, equals 0. Okay, so this one is the tangent plane here. So everything here, yeah, on the close to the close to this point can be approximated by a value on the tangent plane. Okay, so that is the idea. And on the tangent plane, then you have this formula. Yeah. So you see now this one is your h1, and this is your y1. Sorry, your h2. Okay. Then you have nabla f dot h1 h2 equals 0. So just partial f x times h1 partial f times y h2 equals 0. Okay. So you see, so that is why we can approximate the point, the value on the surface by the point on the tangent plane. Yeah. And that is exactly here. So here you just have, you know, the value. So the value at the point x1 plus some increments, some very small increments, yeah, can be approximated by the value of the point plus, you know, this one on the tangent plane. Okay. So that is how it works. So now, for example, suppose you have f of x1, x2 is two variables given by this formula. Yeah. Then, you know, suppose the point is 1 and 2, and you increase x1 by 0.1, increase x2 by 0.2. Okay, then the value, you know, so in this case, then you just plug in the formula, then the partial derivative, so partial derivative with respect to x1, you know, it just, so let me do this calculation, yeah. So suppose you have f of x1, x2 equal x1 square plus x2 square plus logarithm x1, yeah. Then partial f with respect to x1, okay, it's just equal to 2x1 plus 1 over x1, yeah. And partial f with respect to x2 is just 2x2 plus 0, okay. Then what is partial f with respect to x1 is 1 and 2. So partial f with respect at 1, 2 will be 2 times 1 plus 1 over 2, right? Sorry, 1 over 1, yeah? Because x1 is 1. So it will be 3, yeah? And partial f with respect to x2 at the point 1, 2 will be 2 times 2 will be 4, yeah? So now your increment is, so your increment is 0.1 for x1 and 0.2 for x2. So now when you plug it in, so f12, no, 1 loss plus 0.1 partial f 1 at 1, 2, 0.2, 1, 2. So So it will equal, so this one will be so this one, so f12, you put in 1 here. You got 1 square plus 2 squares equal 5, yeah? And this one you have 3, yeah? And this one you have 4. So you have 5 plus 0.3 plus 0.8. So it will be 6.1, yeah? So that is how I got 6.1 here. And you see that if I use the exact calculator, I put in the calculator, if I put 1.1 for x, 2.2, I mean 1.1 for x1 and 2.2 for x2, then I get this number, 614 something. So approximation is pretty good. So approximation is 6.1, so it close, I mean it get to the first digits after the dot already, yeah? So the approximation is pretty good. So now, how do we use this to derive Newton method for n variables? So now suppose I have a n system. Okay, so n nonlinear equations. Okay, f1 to fn. And then I have n unknowns. Okay? Then it equals 0. So now suppose x star is a solution. So now my x star is actually a vector. Is, you know, like x1 star up to xn star. Yeah? Is the solution. And then the kth iteration is denoted by this. So x1, but then the superscript is k. Is the kth iteration. Then remember by the formula, by the Taylor formula for n variables. Okay, so the n Taylor formulas can be written like this. So before we have before, what do we have here? Before we have x1 plus h, remember? Yeah? So the formula before we have something like this. So I want to use this formula. So for okay, so this is my formula, yeah? Okay, so I want to use that formula to derive, you know, the first line here. Okay, so why is that? So now, if I choose this one to my x star, yeah, so this one will be x1 star. So this one, so x1 plus h1 to be x star, but the first component. Okay. Then what is h1? So h1 will be x1 star minus x1. Okay. So remember x star, okay, is a vector, is x1 star, x2 star up to xn star. Yeah. So now I plug it in. So now if I put it in here, so here I have, so plug it in here, that I have f x1 star up to xn star. Right? Yeah, I plug it in here. Then on the right hand side I have f of, you know, instead of x1, then I have so Okay, so just put x1 here, yeah? Just put x1 here, yeah? So because this one is still x1 up to xn. Okay, but now instead of h1, now I have x1 star minus x1, yeah? I just replace it and partial f with respect to x1 and so on, yeah? So plus, so hn will be xn star minus xn partial f with respect to xn, yeah? You see, so it's similar to this equation. It's similar to this equation. Okay? Well, accept the superscript k. But you know, the superscript k, you know, you can fix it easily because, you know, the x1 here, you can put a superscript k here. That is how I derive from here to here, yeah? So the key, the key is just this one. So you agree that from the previous equation I can get this one, yeah? And now, because I have n equation, remember, we have n equation. So this one is only for one function f, but I can have n function f, so then I have n equation like this. Okay, by using the same formula. I can write, you know, just repeat, you know, this one, instead of f1, I have fn. Okay, so far so good, yeah? So this one was derived from the Taylor polynomials, from the Taylor expansion for the function in n variables. And this one applied to function f1, and then up f2, then up to fn. Yeah? So far so good, yeah? So we have this system. And now, let me rewrite this system a bit further. So now, so I just put this one to be f1, yeah? So I have f1 here, f1 here. So this one f1, f1, and you know, I'm in the iteration k, so put to be iteration k. You know, because you have many iterations, so you replace x by xk, yeah? So you have fn x1 star up to xn star equal fn x1 to the k xn to the k plus x1 star minus x1 to the k partial f1 of x1 dot fn star minus xn to the k partial fn, so this is fn, yeah, of xn. Okay, so now this is a system. So now on the right hand side, remember we assume that x star is the solution of the linear system, I mean a non-linear system, so those are equal 0. So I have a big 0 vector on the left. Okay, I want to rewrite this in terms of matrix multiplied by a vector. Okay, so the right hand side this equals 0, yeah. And now I want to rewrite the matrix. So now look at the matrix. So so now I will have. So the first will be a vector f1 and x vector k up to fn x vector at k, yeah, plus a matrix multiplied by a vector. So the vector will be x1 star minus x1 to the k up to xn star minus xn to the k. Okay? And so what is the matrix? So the matrix is just partial f1 with respect to x1, yeah? Partial f1 with respect to xn, and then partial f2 and so on. So the last one is partial, so dot here, partial fn with respect to xn, and partial fn with respect to xn. You see? So you see that the matrix, you know, you have all the combination of first derivative, you know, of all the component of f with all the component of x. Yeah, so it's become a matrix. Yeah? Question? Yeah, sorry. This one should be x1. Yes, thank you. So partial fn with respect to x1. Yeah, thank you. Okay. So that is exactly the next slide. So the next slide is I have written as, you know, in terms of matrix multiplication. So you see, I mean, I rewrite. See that this one is the right hand side. Yeah, the right hand side is 0. Well, but it was here, so it was 0 here, so 0, 0 here. Yeah. Okay. And then I have f of xk. So this become a vector. Remember, so this is a vector of n components at the xk. Yeah. And plus the matrix. So this is a matrix. This is a matrix. Yeah. Okay. With all the partial derivative with respect to x1 up to xn on the components. Yeah? And this vectors are just x star minus xk. Okay, so you compress everything into a single line. You know, but inside this line, f, the vector f has n components. And the vector xk has n components. And x star has n components. And this matrix has n by n entries. Okay? So you condense, you know, all turn into one line. Yeah? Compress into one line. Yeah? And what is the name of this matrix? Jacobian matrix. Yeah? And you see that, yeah, so this one is a Jacobian matrix. And you see that now, if I solve for this, so if I solve for this equation, then this is how I get, right? Because you see how I solve this one? So now suppose I have, so suppose I have this equation x, so this one is a vector, yeah? A vector. Okay, so Jacobian, yeah, at x to the k vector, x star vector minus x k vector equals 0, yeah. Then I move this one to the left, yeah. So I have j, so this one multiply, okay. So jf multiply, no, yeah, jf evaluated at xk. It's a matrix, then multiply x star minus this one equal minus f xk vector. And remember, because it's a matrix, you have to multiply by the inverse of the matrix. Yeah, so you got x star minus xk is j inverse f xk. Yeah. And do not forget the minus, because there's still a minus. Yes. And then now you have x star, you know, is, you move it here, so become xk, yeah, minus Jacobian x to the k f xk. Okay, so that exactly this line, yeah? So I assume that the Jacobian is invertible, otherwise the inverse doesn't exist. And now this is the Newton method. So if you go to this one, you replace this x star by x to the k plus 1, the next iteration. And you see, now if you remember the very first formula for Newton method. So when you have only one variable, Then what is this one? So it is xk plus 1 and xk, and what is this one? Just the f prime. Yeah, so just f prime. So you see now, when you generalize it, then the f over f prime become the f time, well, it's actually become the inverse of the Jacobian multiplied by f. But you see, everything now is a vector. So this is a vector, this is a vector, this is a matrix, inverse matrix is a vector. Okay? And now the algorithm is you choose the initial guess. So your initial guess is not one single value, but will be n values, n real values, initial vectors. And then, you don't want to compute the inverse of the matrix because sometimes it's very ill-conditioned. So what you do is you just solve the linear system. You solve the system, JD equal minus F, but essentially D is just the inverse of the Jacobian multiplied by F, yeah? But, I don't want to compute the inverse explicitly. And then I modify xk minus 1 is xk plus this solution. Okay? And so on. So now, we never compute the inverse of the Jacobian. Okay? So you see the method now? Question? Yeah. No. So this parenthesis just means the iteration. See, k is the iteration. So k equal 1, equal 2, equal 3. So you see, so that's why it's not the power, it's not the derivative. It's just the iteration. You denote the iteration. Because if you don't have a k here, then you confuse the k here and the k plus 1 here. Yes, because you use the subscript for the component. Yes, so that's why I have to use a superscript. Yes, very good point. But it's a notation, yeah, because before you don't have that problem. You can use it as a subscript. You can use it at the bottom, yeah, xn plus 1 equal xn something. But now your bottom, the bottom used for the component of the vector. So you have to raise to the superscript. Yeah, the superscript is just the counter. You see, so that's why initial guess is here. Everything is 1 here, yeah, but it has n components. Okay? Yeah? So that is how it works, and now we can see the example. So that's the theory, and now you can see it in practice. So suppose you have a two equation like this. So it's nonlinear, so you cannot use linear system to solve it, right? So you have x1 square, x2 square here. And initial guess, I just put in 2 and 4, yeah? And so this is like the first equation and the second equation. And when k equal 1, okay, then you can compute x1 to be like this. And the Jacobian, okay, so what is the Jacobian in this case? So the Jacobian in this case will be, so Jacobian in this case will be so you have f1 equals something. So x1 square plus x2 square minus ax1 minus 4x2 plus 11, right? So partial f1 with respect to x1 will be 2x1 minus 8, yeah? And partial f1 with respect to x2 will be 2x2 minus 4, yeah? And then you have f2, so f2 will be x1 square plus x2 square minus 20x1 plus 75, right? So partial f2 with respect to x1 will be equal to x1 minus 20, right? And partial f2 with respect to x2 will be 2x2, that's it, yeah? And so now the Jacobian will be partial with respect to f1 with respect to x1, partial f1 with respect to x2, and partial f2 with respect to x1, partial f2 with respect to x2, right? And you plug it in, so you have 2x1 minus 8 and 2x2 minus 4, and this one is 2x1 minus 20, this one 2x2, so the Jacobian. But what we need to do is we need to evaluate the Jacobian at x1, yeah? So x1 is 2, 4, so when x1, well, x1 upper script 1, yeah, will just equal to 4. So then, so add this one, yeah, then the j will equal, so now you have to plug it in, so you have to plug it in here. So 2 times 2 minus 8, okay, and then 2 minus 4, and 2 times 2 minus 20, and 2 times 4, okay, and so that is how I get, so this one will be minus 4 plus 4, yeah, so minus 4, so it's good, minus 16 and 8, yeah, so that is exactly how I got this Jacobian, okay. You see, I have to do some calculation before I implement it, because if you implement it and your program doesn't work, then you have to know what's wrong, yeah? But at least you should do like 1 or 2 calculations. Okay, so let's say my Jacobian. And then I have to solve, so remember the Jacobian I have to solve, you know, so I have to solve GD equal F, GD equal minus F, yeah? So I have to solve. So the next step is you have to solve this. So D will be, so JD equal minus F at x1, yeah? So this one D1. Okay? And remember the matrix D, so minus 4, 4 minus 16, 8, and then D1, 1, D2, 1 equal, so the function F is 1 minus 55, yeah, because, and then you get out this D1, okay? So you get out D1 like this, so you don't have to solve it. You know, you can solve it by MATLAB, and you plug it in, you got x2. So x2 is just x1 plus d1, and then you got fx2, and you got the Jacobian at x2, and so on, yeah? So now, you know, I mean, after a few iterations, you see that your solution, so here you start with 2 and 4, right? After 8 iterations, then it converts to something. So 6.535, 3.605, and you see the value is very close to 0. So you know, 10 to the minus 12. Okay. So now let me implement it by MATLAB, the process, yeah. So we just follow exactly here. We follow exactly here, but we just implement MATLAB. So we make a new script. Okay, so I define so we just define f to be so x1, x2. You see, you don't have to define. You don't have to define as f1, f2. You can define as a vector as well, right? So what is your function? So the function is maybe let me put into the. So remember, what is the function? The function is f1 and f2, yeah? So f1 will be, so you can define anonymous function like this, yeah? So this one maybe we save as, or maybe later. But you see, define the function first, yeah? Define the function. And so remember, your f1 is just x1 square plus x2. You see, so my x can be a vector, yeah? Vector 2 components. I define it like this, yeah? Minus a x1 minus 4 x2 plus 11, yeah? And my second equation will be x1 square plus x2 square minus 20 times x1 plus 75, okay? Yeah, so this is how I define my function. So you see, my function take an x as a vector and it return a two columns. I mean one by two. Well, what is a vector? You know, two components. Yeah, okay. And then you can define the Jacobian. So I define JF, and I can take in a vector x as well. So define the Jacobian. So I define JF to be, you know, you can take in a vector and then 2x1 minus 8 to x2 minus 4 and 2x1 minus 20 to x2. So this is my Jacobian, yeah? And now I just implement the method. So for k, so I just define x0, well, sorry, x1 to be 2, 4. Remember? So this is initial guess. So this one initial guess. And now carry out the iteration. So Newton method. So I just say that, okay, for k equal 1 to say some iteration, say 15, or you can say that n max, you know, so n max will be 15. So the maximum number of iteration and you see iteration. See, the algorithm said that at first you have to solve the vector d, yeah, so you have to solve d equal j f at x1, yeah, backslash f at x1, right? So this is exactly the formula. And then, well, maybe Maybe I don't have to write x1, you just write x. Because I will reuse it again and again. And x is x plus b. But then I forgot the minus. And that's it. So this is a formula. Okay? And let's see whether it works or not. You define the function, yeah? Define the Jacobian, and then you define the formula. Okay? So now, whether this works or not, yeah? So save it. So they want me to save it, so I save it like test Newton 3D. Now I run it. Okay. So now how do I know it works or not? I have to check the vector x. Yeah. You see, so the vector x after the 15 iteration give me this. Yeah. And now I just put in f of x close to 0. So it's good. So everything is correct. But sometimes, sometimes it's not going to be easy. Sometimes, you don't get exactly what you want. Then you have to trace back, on the calculation. In this case, everything just follow, right? Because we did on the preliminary works already, so we know everything, right? And you plug it in, and then it just give you the solution, okay? But what happens if you just say, you miscalculate the Jacobian? You miscalculate the Jacobian, then you don't get what you want. Suppose I put like 8 here, right? I forgot to put in here, okay? And what is going to happen? Well, I just still run it, right? But when I run it, then unlock, yeah. So when I run it, then I get x to be something different, right? And then I evaluate f of x. I got only 10 to the minus 3. You see? So you see, so then you have to go back and do all the calculation and check what went wrong. Yeah. So that's why it's still very good to do the calculation by hand, at least for the first iteration, and then after that you plug it in and you get exactly here. And secondly, the initial guess is important as well. Because now you see that initial guess you have 2 and 4 close to this number. But suppose I put in like say minus 20, say this one 40, okay? And let me run it. Yeah, so then I have x equal, so it's still close, yeah? But now what is it's still pretty good, okay? So in this case, then it's not very sensitive to the initial guess, yeah? But you see the idea, right? So any question in this? Yeah?
If you run a lot of iterations, does it eventually become less relevant when finishing S-curves?
It depends on the equation. I don't know. You see, because you can see that, well, that's why we have the number maximal iteration. Like suppose some good equation, it gives you a solution after like 10 or 20 iteration. But some bad equation, you can change it. It might give you like a million iteration to get to the correct solution. So it depends, you know. So for the last minutes, I will tell you that in MATLAB there is a solver for system of nonlinear equation. They call it fsolve. So you see, so you can define your function as, you know, like, so in this case is two variables, yeah, so x1 and x2, yeah, and then output is a 2 by 1 vectors, yeah, and then you call fsolve. So it solve it, you know, by a combination of Newton method, and so in some sense you don't have to worry about solving a system nonlinear equation when you have MATLAB, okay, because it did this for you already. So you just have to define the equation, yeah. So the equation can be complicated like this, okay, and then you have to give the initial guess, okay, and you pass in the function, you define it, and you pass in the function, and then it gives you a solution. So inside, just do Newton method and another methods as well. So here it say that well, so it has a few algorithms. Let's use Leeuwenhoek-Marcotte algorithms. I think they use a modified version of Newton method, okay? Because it still need a Jacobian, so it still need a Jacobian. So it use the transcription algorithm. I think they use a modified version of Newton algorithm, okay? And you are going to need this one for the project, okay? So for the project, there's some part you need to solve a system of nonlinear equations, and either you can implement Newton method yourself, or you can use fsolve. And in some years, I saw people use fixed point iteration. It's still okay. Fixed point iteration, you can use it for a system of 2 or 3 equations as well. Okay. Okay. So any question about this chapter? So otherwise, then we stop here. And remember, there's no lectures next week, okay? But the tutorial is still on, lab is still on, and lab submission next week, okay? And there will be a lab test in week 7 as well. I will give some details, okay? And the question? No, okay? No, it's just interpolation. The next one will be nonlinear equation. For next week. Yeah, for next week. The newest lab, yes, the newest one. Yeah, interpolation. The nonlinear equation. Okay? Oh. Yeah. Yeah. Well, I have to pick up the desk. I have to go to my office. I gotta do this. Yeah, we go.